Okay, class, hi. This is the promised video tutorial for conducting your secondary data analysis. So the first step will be to log into the virtual computer lab. You can just simply go to Google and type NYU VCL, and then from there you'll click on the link there. It'll open in another window or perhaps just link you right to it. And then you'll, after authenticating, you'll click General Use, GIS, and Data Analysis. And then that'll open the virtual computer lab. Um, from here, I've seen it take sometimes up to 2 minutes for it to load, but just be patient. And once it loads, it should look something very similar to this. The next step is to go ahead and move the files that you have on your computer. So you should have had the actual data set. I'm posting the Stata version and not the Excel version, and something called a do file, which are necessary files for Stata. That way you don't have to convert the spreadsheet into Stata. So just saving a step. So you'll download those from the NYU Brightspace, and you're going to have them on your computer. And please know where they are, because you're going to click here where it says My Files, and we're going to click Temp Files here. Since the folder is empty, just drag files here to upload them to the virtual computer lab. So we're going to select the data set, which is a .dta file, and then the Stata do file. So we're just going to drag those in to this box. So that's our do file. And then we want our data set here. It'll be a little tricky dragging it. There it goes. So that's it. So they are now in the virtual computer lab. So we can close out of here. And we're going to select Stata from this drop down on the side. Scrolling down, Stata version 18. Of course, it's the last one. I'm going to go ahead and make it full screen by clicking these two arrows. It's resizing. I'm going to drag it down a little bit just for my own comfort. So from here, we're going to go ahead and open our file. So we can just click on this little folder on the left. And then we're going to select our directory of temporary files on the left. And we're going to open our, it really doesn't matter what order you go in. It shows here the Stata data set is first. And so we can click that and then select open. So now we have all of our files, all of our data set is now into Stata. So let's go back one more time to the open file, and we're going to open our do file. And here we go. So it's going to open this. This is kind of like a little notebook of what you can create. That way you don't have to type everything here into the command line. That way, if something doesn't work, you can just continue to edit it until it does work. And then it leaves a paper trail. So at the end of the day, once you're done with your analysis, you can save it, and that way it has a paper trail in your notes of everything you did today. And that way tomorrow, if you have to go back and change some things, you don't have to start from scratch. Okay, and so one last thing I want to do is open a log file. And so to do that, we go back into this left-sided window here. And here we go. Right here, it's this little notebook icon, log. So we're going to click it. It wants you to, so first I'm just going to make sure we select our temporary files directory. And for the name, we're going to name it. You can put your name, David's log file. And I'm just going to put today's date, 2023.0909. And that's it. I'm just going to put save. And when we're done, after all of our work today, we're going to now download this to our local computer, our regular computer. That way we can have a good output of all of our hard work, because this really is hard work, and you'll see much more of that later. So getting started, so I already created our little notebook here, our do file. So I want you just to, you really should get in the habit of being as professional as possible when it comes to your work. So it's good practice to label it with your class name, your professor's name, and the more detailed, the better, because sometimes in real life, like for example, my dissertation took several years. And so I started at one point, I had no idea it was going to take as long as it did. And so it was really good that I was trained to be as, as thorough as possible, because you really want to go back and be able to find exactly what you did and how you carried out your analysis. So step one, we think we've already done it all. So what I've written here is we'll upload our DTA file, which is our data file. So that's done. We've done our do file. So that's exactly what we're looking at here on the right-hand side. We've opened our files in Stata already, and we opened a log file and named it. So that's really how you start. Okay, so next we're going to go ahead and get started with the data. So step two is to describe the data set. So one command that allows us to describe our data set is the describe command. So you just type describe, comma, short, and we'll highlight this, and you can do Control D, and it's going to carry it out on the left side window here. So we'll say Control D. So what this tells us, I'm just going to click to the window underneath. We have 403 observations and 20 variables. Okay, so that's basically 403 participants and then 20 variables. And you have 20 variables because that's what we had in the code book on the assignment. Okay, however, when I went ahead and cleaned the data as much as you needed it to be, and rename some variables so it was cleaner, because there were some text variables and you have to convert those. And I just saved us a step and did that already. So this is a cleaned data set for the most part, but it still has some things that we're going to do together as an exercise so you can get familiar with Stata, so you can conduct your research analysis. So now that we know we have 403 observations and 20 variables, the next step that you'll want to do is create new combination variables that are clinically relevant to your research question. So we know if we just, I'm going to open this up again. So we see here, I'm going to toggle it to go ahead and alphabetize. We have age, we have blood pressure, diastolic, systolic. So there were two readings there. We have cholesterol, we have body frame, we have gender, binary, male and female. We have a hemoglobin A1C, we have HDL, we have height, we have a hip circumference, we have the ID of the participant, we have the two locations, we have a waist to hip ratio, I believe. We have a variable I created called ratio verify. And then we have glucose, we have waist, and we have weight. So we have several variables here, but what we don't have is BMI. So let's get started by creating a BMI variable, just to show you how to create a variable in Stata. Oops, actually, I went too far. So actually, first we're gonna go ahead and see, let's see here. So we have our ratio variable of cholesterol divided by HDL. So one second. Okay, so I was just verifying in the code book. So we have this variable of ratio, which is actually cholesterol divided by HDL. So let's go ahead and recreate this variable just for an exercise so we can verify to see, in fact, like, do we get the same calculated version that's given to us from the data set? And we'll call that ratio verify. So when I reviewed this just a second ago, I saw we had ratio verify already. So I'm just going to drop that variable, right? because I cleaned the data already. So I forgot to delete that from scratch so we could start the exercise. But so we'll generate. So in order to generate a variable in Stata, we just simply type the word generate, and then we think of a variable name that'll be, that we'll be able to decipher later on. So I'm going to call this ratio under verify. And so we say generate ratio under verify equals cholesterol divided by HDL. So these are the variable names that we have in our data set already. We have cholesterol and HDL. Just want to show you that here. So we have cholesterol and HDL. So that's given to us. So let's highlight that. And then we're going to say Control D. And we were able to generate it, and we had one missing value. Okay, so perhaps one person did not have either cholesterol or HDL logged in this data set. So now let's go ahead and we're going to compare the ratio that's given to us in the data set with our ratio under verify variable that we've created. That way we can see a side-by-side comparison. So let's highlight this here. And we use the list command. Okay, so we're going to say list ratio and the ratio under verify. And let's say Control D. And now we see here, I'm just going to scroll to the top, and my mouse is pretty quick. So let's see here. Went too far. So here we see the original variable of ratio and then the one we created. So Stata really carries out a lot of decimal points, but you can see that they basically coincide. So 3.59, which is the variable that was given to us, and the calculated version was 3.625. And so you see some correlation there, 6.9, and then really if you round up here, it's 6.9, and so on and so forth. So we know that we created a variable, and that's the first variable that we created in Stata. So next, now we can get to the BMI example. So the mathematical formula for the BMI, I just went to the cancer.org website, and we got the BMI formula here. So it's weight in pounds, and that's what's given in our data set, multiplied by 703. And then you divide that by height in inches and you square it, okay? And then the different categories for BMI are underweight, normal weight, overweight, and obese. And then they give you the different criteria there as well. So just scrolling down here on our do file. So remember, we're going to say gen. So gen is just, so Stata will accept either the word generate or gen. Okay, and then we're going to call the variable, our new variable will be called BMI. And then we say equal, and we use parentheses, and we put weight, that's the name of the variable that we already have, times 703. Let's close the parentheses, put the division sign, and then we're going to open parentheses and another parentheses and put the height variable. We're going to use the caret symbol, which is located with shift number 6 on your keyboard, and then we're going to close the parentheses. So by doing that, we're going to create a new variable called BMI. So let's do Control D. And we see it generated the variable, but it tells us we had 6 missing values. So 6 participants either did not have weight or height collected, okay? So what you can see here is there is some missing data in this data set, which is quite common. So let's go ahead and verify our new variable. We're gonna say list BMI, and we can say Control D after highlighting it. And just by scrolling up, we're gonna see these are all the new BMIs that we created, okay? And I'm just scrolling here. See, now we see dot here. So participant number 87 has a missing data there. So just FYI. So that's how it looks. I'm just going to scroll down so we can move along. And then let's say we want to get a summary. So for our descriptive statistics, in order to get like mean and range and mode and all of those important descriptive statistics, we just say sum or summary, and then we'll type our variable name of BMI. It is case sensitive, by the way. So you always have to follow exactly how you created your variable, and then we'll say comma detail. So we'll highlight that and say Control D. So you can see here, so a summary of BMI, we see the mean is 28.78. We had 397 observations, right? Because we had missing data. We have our standard deviation and so on and so forth. So what if we wanted to look at BMI by location, right? So we have this one variable called location under cat for location categories, where we have 0 equals Buckingham and 1 equals Louisa. So you don't have to take my word for it. I'll show you how to verify. So we can say tab for tabulate and then location cat, which is our location variable. We'll highlight that and say Control D. So we see here location for Buckingham, we had 200 participants, and that's 49% of our data set. And then for Louisa, we had 203 participants, and that's 50% of the data set. Okay, but what if we want to know how these were coded? So we can drop those labels. We'll say tab location cat, comma, no label, and that's going to remove the Louisa and Buckingham. So let me just highlight that and say Control D, and now you'll see it dropped the labels, and now we can see Buckingham is coded as 0 and Louisa is coded as 1. So everything is coded in Stata. So that's something you have to get used to, and it starts with 0. In other programs, they might start with 1, but in Stata, we always start our coding with 0, okay? So next, we can repeat the process, but if we use the if command, which is to tell Stata we want to look at a certain category, we have to use the double equal sign here. Okay, so here we're going to say sum for summary, BMI, if location cat equals 0, and then say comma detail. So that's that's the syntax for Stata. Let's say Control D there. And so this is what happens. So for this first location here, we see they had a mean BMI of 28.58. So let's compare that with the next location. We have the exact same thing. You could just cut and paste and then change the code for location to 1 and say Control D. It's almost identical, right? So we see here 28.58 for the location coded as 0, and then 28.98 for the BMI of the location coded as 1. So again, just as a syntax note, you might be curious as to why there's 2 equal signs there. So anytime after the if command, you have to use equal equal. Okay, it's just a convention of Stata, and that's all I have to say about that. So I'm just scrolling down here. So next we want to, let's say we want to create those BMI categories that were available from our citation there. So based on what was from the literature, we can code underweight as 0 and normal as 1, and then overweight as 2 and obese as 3. Okay, and we'll call this variable BMI under cat, denoting BMI categorical. Okay, so the first step when you always create a variable, you say gen or generate, and then your new name, which is BMI under cat, and then we say equals dot. Let's highlight that and say Control D. So we created 403 variables here. So next we're going to replace BMI under cat equals 0 if BMI is greater than or equal to 1 and BMI is less than or equal to 2. Less than 18.5. Sorry, long day. So our range, right? So you'll see here, we kind of have arbitrary numbers. Nobody had a BMI of 1, but we just need to tell Stata we're going to look in the window between 1 and 18.5, right? And notice we're using just the less than sign. And here we're saying greater than or equal to, okay? So you have to kind of recall what those mean for math. So let's go ahead and carry this out. We're going to highlight it and say Control D. So great. So we made 9 changes there. There were 9 participants who fell in that category. So next we're going to type replace BMI under cat equals 1 if BMI is greater than or equal to 18.5 and BMI is less than 25. So let's highlight that and say Control D. And then we're going to do that for the same remaining 2 categories here. So I'm just going to highlight that so we can move along. I've done the work for you. You're going to go ahead and create your own variables later, and you can just copy paste and follow this same convention for yourself. So I'm going to say Control D. And now we've done category 2, we had 123 changes made, and category 3, 152 changes made. All right. So just to reiterate, we have, remember I picked arbitrary values of 1 and 99 for our low and our high, just so we can set some parameters for this categorical variable, just really so we can program Stata to think the way, we have to think the way the computer thinks, really. So next, as a rule for good data management, we need to label our variables, okay? Because right now, it's not gonna have anything. And when we go back to this variable, it would be nice if we had our categories labeled. So to do this, I really just, downloaded this recipe from the internet. So first you say label variable BMI under cat, and you put quotes, and we'll call it BMI categories. So we're going to highlight that and say Control D. So it carried it out. Next, we say label define BMI cat and 0 and quotes for underweight, 1 quotes for normal, 2 quotes for overweight, 3 quotes for obese, and then we say comma replace. So we're going to highlight that and say Control D. Next, we say label values BMI cat and BMI cat. And this is just the recipe that you have to follow. And next, let's see if it worked. So we'll say tabulate our new variable BMI cat. We're going to highlight it and say Control D. Perfect. So now it's labeled really nicely. It says BMI categories. We have underweight, normal, overweight, and obese. And you can see your frequencies and your percentage. So these are your descriptive statistics. So this is exactly what you will be using. Perhaps you might not be using these very same categories. It really depends on what citation you're using and what's pertinent to your study or your QI project. So now can we look at BMI categories by location as we did earlier? So we can certainly say tab BMI cat if location cat equals 0. So let's see what happens when we do that. We say Control D. So now this is just for the location coded as 0. We can see there was a little bit of a difference here. If I just scroll up, we have 397 overall and 197. And this is the breakdown for location coded as 0. Next, let's do the location coded as 1. We say tab BMI cat if location cat equals 1. And it's highlighted. Let's say Control D. So now we have 200 participants in this location, and these are their BMI categories. Okay, so that's one way of doing it. That might be pertinent for another type of variable you're looking at, but you can always do what's called a cross tabulation. So simply you're just going to type tab BMI cat location cat. Let's highlight that and see what that does. So we'll say Control D. So this is actually much better in my opinion. So now we have in one column, we have our BMI categories by our location categories. The only thing that's missing here is we have some frequencies, but we don't have percentages. And when you read research studies, you're always going to see the frequency and the percentage. So to do that, we're going to repeat this. We're going to say tab BMI cat, location cat, comma, and we're going to add the word row call for row and column, okay? And it's going to add percentages that we need. So let's highlight that, execute it, say Control D. Beautiful. So now we have our categories here, and we have our locations, and now we have our row percentages and our column percentages. So if we look at Buckingham, 3% were underweight, 31% were normal weight, 403 were 43 were overweight, etc. Okay, so let's say we want to create a list of these two just so we can verify, like, do our BMIs fall within the correct category? We can say list BMI cat and BMI. Let's highlight that and see what that does. So these are all of the various BMIs from our entire data set, over 400 participants. Sorry, I went too far. My mouse is way too fast in this computer lab. So we have BMI cat here and BMI, and we can see normal 22, obese 37, and so on and so forth. So it looks just, on the surface that everything was carried out correctly. Good. So let's move on with our do file here. So 3B is an example for the waist to hip ratio. So we can certainly create a waist to hip ratio. We have cutoffs by sex given by the World Health Organization that define abdominal obesity in men as a waist to hip ratio of at least 0.9. This is just an example. Next, we have for women, it's a ratio of 0.85 or more. They also state that a ratio higher than 1.0 for either sex means a much higher risk for health problems. Okay, so let's run with that. We're going to generate the waist to hip ratio. We'll call it WHR, and we're given the variables in our data set of waist and hip. So to generate that, it's just a ratio. So we'll say gen WHR equals waist divided by hip. We're going to highlight that, say Control D. It went ahead and generated that variable, and it says 2 missing values. So 2 participants either did not have waist or did not have hip measurements. So let's verify. We can say list WHR to see our newly created variable, and we'll say Control D. So here, I don't even have to scroll up. So I see participant number 394 had missing data there. But otherwise, we seem to have all of our ratios. And you can see the different ranges. Really, this doesn't do much for me. I need to see a summary. So let's say sum WHR or summary WHR, highlight it, say Control D. Perfect. So now we see we have 401 obs with data, observations. The mean was 0.88. We see our standard deviation, and we see our min and max here. So these are perfect descriptive statistics that you could use for your study or your QI project. So next, moving on with this exercise, using the criteria of waist to hip greater than 1, we could create a categorical variable for high risk, as we did for BMI. So to do that, we'll call it WHR cat. We'll say gen WHR cat equals dot. So let's highlight that and say Control D. So we have 403 new variables created. We're going to replace WHR cat equals 0 if WHR is greater than or equal to 0, and WHR is less than 1. Okay, and that's just based, so I'm using arbitrary numbers again. We see our low end here was 0.68. So we know nobody had a waist to hip ratio of 0. And then we're looking for anything less than 1 for this first one. So we're going to highlight that, replace. Here we go. Let's say Control D. Great. 397 changes. That's a lot considering we just have over 400. So let's do replace WHR equals 1 if WHR is greater than or equal to 1 this time, and less than 2, because nobody had a waist to hip of 2 as our high end. Let's say Control D after highlighting it, and we got 22 changes made. So next, let's label this newly created variable as we did before. We're going to say label variable WHR cat, and then we'll say quotes waist to hip ratio categories. So let's do that. Control D. Now we're going to say label define WHR cat, 0 quotes normal risk, 1 high risk, comma replace. Okay. Control D. And then we're going to label values, WHR cat, Control D. And now let's see if it paid off. So we'll say tab WHR cat. That's our new variable. Beautiful. So here we see waist to hip ratio categories, normal risk and high risk. However, is this clinically significant? Really, we just saw that the majority of the sample had an obese BMI. And now we're saying the waist to hip ratio was normal for 94%. I don't think so. So perhaps this isn't a good indicator, or maybe we just didn't categorize it effectively. So this is just a good example of what you can do, and it's always trial and error, right? So perhaps we have to use the gender-based parameters of what is it, 8.5 for women and 0.9 for men, to see if we can get some better, some better clinical significant variables here. All right, so moving on. So let's say we want to just go ahead and look at, we'll do a cross tab here. So let's say we'll do tab, WHR cat, and gender binary. So let's look at that. We're going to highlight it and do Control D. So now we see in one column our waist to hip ratio and our gender. So normal risk, we saw 226 females and 153 males. And for high risk, 7 females and more males, 15. Again, remember, when we have frequencies, we should probably have some percentages too. So this time we're going to say tab WHR cat and gender bin, comma, and I'm just going to say column because I really don't want to see the row percentages. Let's just look at the column percentages here. It's up to you, but let's do Control D here. So now we see 97% of females were normal risk in our data set, whereas 3% were high risk, okay? We'll take it with a grain of salt. So in the next example, we're going to look at age categories. So let's say you're concerned that emerging adults in your practice are increasingly becoming obese, and you'd like to examine if obesity in this age group is associated with CVD risk factors. So let's get some general statistics, some descriptive statistics of the ages in our data set. So we'll just say sum for summary, and then age is the variable that's in our data set, and we'll say Control D. And here we see 403 OBS all had their ages collected. The mean age was 46.85. We have our standard deviation, and we see the lowest age was 19, and the highest age was 92. Okay, so let's say we want to create some categories, just whatever, 19 to 29, 30 to 39, etc. So we're not going to change our original variable. We're going to create a new one as we've been doing, and we'll call it age cat. So just as before, we say generate or gen age cat equals, and we're just going to say dot, we're going to say Control D. And we've got 403 newly created values. So now we're going to do as we've done before. You could just copy and paste from above and then change the variable to age cat, and so on and so forth. Change the coding from 0 to 7, and then so on and so forth. So we can do this one by one as we've been doing. So let's go, we're going to highlight for the first category of age cat equals 0 for the ages 19 to 29. And we're going to say Control D, right? We have 66 changes there. So we have 66 people in that category. That's a good chunk. So we'll do the next one, Control D, 78 changes made. We'll do the next category here for 2, and that's for 40 to 49-year-olds. We had 88 changes there. So now we have for category 3, between 50 and 59, Control D, we have 69 changes there. For category 4, between 60 and 69, Control D, we see 62. So we see like it's kind of balanced for the older age groups. So for category 5, between 70 and 79, Control D, 30. So it's kind of like a histogram, right? We're seeing some normality there. It's coming down. We're seeing 30 changes there. For category 6, between 80 to 89, we see 8 changes there. Oops, I think I deleted something. There we go. Next, for category 7, between the ages of 90 and 99, let's see if we're surprised here. Only 2. So, okay, so there weren't a lot of 90-year-olds in this population. So we've done that. So let's tabulate. We'll say tab, age cat, comma, miss for missing, just to see if we have missing data there. And let's say Control D. So we have our 7 categories, actually 8 categories because we're counting 0. We have all of our frequencies and our percentages. When I'm looking at, it doesn't really mean much. Why? Because we didn't label it. So let's go ahead and carry out our labeling here. Just going to scroll down. So we say label variable age cat and then quotes age categories, Control D. And then we're going to say label define age cat, and we're going to say 0 for ages 19 to 29, 1 for 30 to 39, and so on and so forth. And then we say comma replace. It got truncated and moved over, but I just want to make sure you follow that when you do your own creating of variables. So we'll say Control D here. Done. So now we'll say label values, age cat, and we say list age and age cat. So now we're going to make a list, and we're going to put the original age variable against our new variable of age cat, see if the ages correlate with our new categories. So say Control D. Perfect. So here we can see, let's just scroll up to the top. I'm going to go too fast. Oops, went too fast. Perfect. Here we see, so for the first participant was age 46. He falls between 40 and 49. 29 falls between 18 to 29, 58, 50 to 59. So it worked. We did really good work here in this variable. All right. And now let's just do a tabulate of age cat and missing to see how it looks. Control D. And we have all 403 participants had their ages collected, and we can see now the exact breakdown, and it's labeled very nicely. So these are just examples. Let's go back to our do file here. These are just examples. They're not necessarily clinically significant, but with this information, you're able to create variables such as A1C and hypertension, like some categorical variables that might be of some use to you. Okay, so for example, you could use pre-diabetes, diabetes, uncontrolled diabetes for A1C. And for hypertension, you could follow pre-hypertension, stage 1, stage 2, or whatever is the most current, classifications for these two disease processes here. So next is the analysis. So really what we covered is just really descriptive statistics. So just to wrap up, this is actually one of our final steps here. So really assuming you've already developed your research question, your hypothesis, you've conducted your review of the literature, you've cleaned your data, you've made new variables. The next step is to carry out your analysis plan, right? And so you really have to be methodical when you do this. So let's move from our example from the first class in which we looked at the Hep C QI study from one of your DNP colleagues. The DNP student was conducting her QI study, and she described her associations using the chi-squared test and p-values. So, so trying to think back to your statistics that you took before, can we examine associations using the chi-squared test for variables measuring A1C and BMI? So when we do that, we just simply say, tabulate, and this is our variable for A1C, it's GLI-HB, and BMI, and we just say comma chi2 or chi-squared. Let's highlight that and say Control D. So too many values. So why didn't it work? So that's really the question here. So when we look into our statistics manual, we see that the chi-square test is only for categorical variables, right? And the A1C and the BMI, those are continuous variables. So you're not going to be able to run the chi-square test. So really your categorical variables that you have are your yes-no variables, your male and female, and then the different age categories. So we have plenty of categorical variables that we've developed thus far. So let's see if we can just use a few to see if we can practice getting a chi-squared test. So we have the age cat and we have gender bin. So we'll say tab, age cat, gender bin, comma, chi2. So we'll type that and then we'll say Control D. Perfect. So this doesn't look much different than what we saw before. We have our age categories here, and we see our gender of female and male, right? But what's different is now we have the Pearson Chi2, which shows 8.84, and we have our p-value equals 0.264. So remember, that's not statistically significant, right? We want our p-values to be less than 0.05. So what this is telling us that there's no difference between these two variables, right? There's no statistical significance when we look at gender and age, right? So that just shows, what we can do here and what we can't do. So what I want you to know about the chi-square test is when I went to our statistical manual, what we saw here is the chi-square test assumes the expected value of each cell is 5 or higher. So if this assumption is not met in your data, you need to use the Fisher's exact test. So when we look back at what we see here with our crosstab, we see here for the ages 80 to 89, and then the male column, we see there were only 2 participants there. And then for the 90 to 99-year-old category, we see only 2 females and 0 males. So we're violating the assumption here for the Pearson's chi-square test, and we need to use the Fisher's exact test. So I have the reference there if you want to go in and read more about it. But the Fisher's exact test is used when you want to conduct a chi-square test, but 1 or more of your cells has an expected frequency of 5 or less. Okay, so that's good to know. So as we saw with our chi-square test results, there's only 2 in the age category for 80 to 89 and 2 or none in the age category for 90 to 99. So let's try to carry out our Fisher's exact test. We do the exact same command. We say tab age cat and gender bin, comma exact for Fisher's exact. Let's highlight that and say Control D. Took a little longer. What we see here is we're given our Fisher's exact test, which is the p-value of 0.287. So for the Fisher's exact, you don't get like a Pearson's chi-squared, you just get the p-value, okay? And in this case, the p-value is 0.287. So you'd say p equals 0.287. There is no statistical significance here, okay? All right, so that's everything. So really in summary, thinking back to our first example of where we tried to examine the chi-squared between the A1C and the BMI, we were not able to run our chi-squared because these are continuous variables. So what do we have to do with this, right? So we now have the knowledge and the skill set to convert our A1C and our BMI into categorical variables that have clinical significance. We can create A1C categories for normal, pre-diabetic, and diabetic, and we can do the same for the BMI categories, underweight, normal, overweight, obese, and then you'll be able to run these associations as your colleague did for her QI project on Hep C. So really the takeaway here today is once you've developed your variables of interest and related to your research question, your background significance, your social determinants of health, you can examine these associations so you can run the results for your QI project. Okay, all right. So let us know if you have any questions. The last thing here is just to close your log. We'll say Control D. After saying capture log close, it closed your log. So you can save your do file here if you went ahead and created some new variables, and then you can save it and we can close it. Same thing, you can save your data set because you did a lot of work in creating the new variables. So you would say save there. Do you want to replace it? You would say yes. I don't. So just say close. Do you want to save? No, I don't want to save. Thank you. So let's just take this out here. So now the last thing you do before you log out, you can click on your files here and you go to your temporary files and we can, now we want to download them back to our local computer. So we have David's log file here that we created. I'm just going to click this hyperlink. It says pop-up window blocked. So what you have to do is you have to click this little, looks like two files on top of each other. You click that, and there, it downloaded it locally to the computer. So what does that mean? So I just want to show you. So this is actually your log file. One second. I'm moving it over. So this is the importance of a log file. I just want to show you. So it really just logged everything you did in your screen from start to finish. So it showed when we started at the beginning, we got 403 observations and 20 variables. We dropped a variable. We compared the variable given to us, which was ratio, with ratio verify. And then after that, we generated a BMI variable. We verified how it looked. Right? We did a summary so we could see the mean, the standard deviation, the number of ops. Then we looked at our location cap variable so we can see Buckingham and Louisa breakdown. Then we said no label so we can see how it was coded. So really, I don't have to walk you through everything, but it really captured everything. That way you have all your descriptive statistics here. And most importantly, you have your results here when we ran our chi-square test, right? So all the way to the end where we got the Fisher's exact test. So, and this is now saved on your local computer. You really want to make sure you have this file because this is what you'll be using for your paper, okay? Let's say you lost this. Well, you still have your do file, right? So I'm going to drag this over. So this is your do file. You have everything here. All you would have to do is go in, reopen everything, and then execute everything the way you did. And then, rerun your analysis. And it's not like you're going to have to start from scratch. Everything's here. You just highlight it, execute it, and it's going to be there for you. But in that case, make sure you did a log file, okay? So that concludes today's video. Good luck and let us know your progress along the way. All right, thank you.